This is our table. I will copy it to another sheet. Let's have it here. So what do we want? We want the total value and we want the mean value with respect to the equal to sum is this sum of all these cells will be equal to 688. Pull it down there is the value of the sum. Now what will be the value here? It will be an average of all four values. So this will be average of these divided by 4 will become your y values. Now if I take overall mean, so that will be the mean of average. There are two ways to calculate this. Either take average of all these values or take an average of these values. So I take the average of all the values just to avoid the confusion. Let's have it a number. So reduce down the values. So this is your overall value. So what are these? So this value is y1 dot and this value is your y bar 1 dot and this value is y bar dot dot. So if we know this, we can find out escape. It is better if suppose we find out y I dot minus y dot dot. So what it will be? This minus this, and because we have to keep this constant, so we will put dollar here and dollar here. This will be the value, and if we pull it over this will be the term. Now what will be sum of the square of this is equal to n is 4 multiplied by sum of now the square of treatment variance. So it will be equal to this multiplied by the same term into that will be over here. So now what will be the total sum of a square of treatment is 4 multiplied by sum of all these values. If I have to find out sum of a square of, to do sum of a square of error, first of all I have to find out yij minus y dot dot, and that is the term equal to this minus this term. I'll put a dollar here to make it constant term, dollar here. Okay, I'll pull it 6 column 4 rows. Now this is now square of this, the square of error will be equal to this multiplied by this, and that we have to pull over 6 column and 4 rows. What will be sum of a square of error? That is nothing but summation of all these values. All these values. Now using this we can generate ANOVA table. ANOVA table. The first column is source of variance. Second column is sum of squares. Third is degrees of freedom. Fourth is mean square. And fifth is F value. Sources of variance, sum of square of treatment, nothing but we call machine, then error, which is sum of square of error, then total, sum of square of total. What will be the treatment sum of square? 533.83. Sum of square of error is 6797.83. Now total will be nothing but equal to sum of these two. What will be this? Error is 5 and this is 18, this is 23. Mean sum of square, this is equal to this divided by this, and the same for the sum of square of error is this. What is F value? F value is nothing but mean sum of square for machine divided by mean sum of square for error. Now this is your F value. Now we have to see whether this F value is, which is a calculated F value, is less than or higher than. Now see the F distribution table for the value of alpha as 0.05, where nu 1 is the degrees of freedom for the treatment, which is nothing but 5. Nu 2 is degrees of freedom for the error. So for the value of alpha as 0.05, nu 1 as 5, this is the column, and nu 2 as 18, this is the row. So where it intersects, we find the value as 2.77. So this is what we call F tabulated value for alpha equal to 0.05 and nu 1 as 5, nu 2 as 18. The value which we have calculated is 0.28. So what we see over here is F table is 2.77 at alpha equal to 0.05, nu as 5 and nu 2 as 18. Now F calculated is 0.28. What it means that F calculated is far less than F table value. So what we see over the F distribution, this is your F table value, and your F calculated will be far over here, somewhere here 0.28, and F table is 2.77. It means that H0 is not rejected. It means that all the machines are producing the rubber stamps of same tensile strength. That was our decision out of the ANOVA analysis. If it could be the case that F value is more than the critical value, then only that case we can say that H0 could be rejected. In this case, we are reaching to a particular decision point that all the machines are producing rubber stamp with the same mean strength. The variability accounted by the change of the machine is not significantly different than the normal variability in the output, the overall variability in the output, which we call error, variability of error, or sum of square of error. So that is what we see. Now in a very short view, I will show how this ANOVA analysis, how this problem can be solved using SPSS.